So welcome back everyone to week 4 of Space Science with Spice. The purpose of this video is to start animating our solar system. So last week we made the function that calculates the gravitational force between two objects or two spheres in Python, and this week we're going to start putting that to use in these things called n-body simulations of solar systems, and we're going to animate using that force of gravity. And as always, I've broken the lecture up into 4 parts, timestamps for each of which, and related links are in the description if you want to skip around. So in part 1, we're going to learn how to animate two bodies. Now, before I jump into the code, just throwing 100 lines of code into your face could be a bit confusing, so I've created what's called a skeleton of a code, or a skeleton of a program. This is something that, especially if you're taking AP Computer Science A or any computer science course in college, or you're just working on your own project that's really long, it's really useful to break up your code into this type of skeleton where you're just defining the different concepts so you have an idea of what each little subsection of your code is going to do before you actually start writing the code itself, and it helps give you an overall bird's eye view of what's going to be happening. So when we're going to start animating, we're going to start with just animating two bodies going around each other, and this is a skeleton for that. So at the beginning, we're going to be declaring our functions, which is the same as always, our force of gravity of B1 to B2. It's the same thing as what we learned in last week's lecture. And then the second part of our code is going to be creating our bodies. So in this case, we're just going to have a star, which is the sphere with the position, mass, radius, and momentum. Now we're going to start denoting momentum with P. It's a bit shorter, and this is what you're going to be using in your physics classes. And we're going to make a planet with the same it's going to be a sphere as well, and it's going to have different parameters, you'll see. And then part 3 is going to be animating with Euler's method. This is what we learned in week 2. You could go back there to get a refresher. And the 3 parts of this, as always, is that you're going to declare a time and a change in time. You're going to make a while loop. You're going to set a rate, and then you're going to calculate the force on each body. So body in this case is just going to be the star and the planet. You're going to calculate the net force on each of these, and you're going to calculate a new force every frame, which is depending on just the distance of them. You're going to calculate a momentum based on the force that you just calculated and the prior momentum of the object, and this is the same thing we learned in week 2, old momentum plus force times our change in time. And then we're going to update our position using the momentum that we just calculated and the prior position. So now that we've jumped over to our code, you can see how, again, these hash marks just indicate a comment. Anything that comes after a hash mark is the computer isn't going to read it at all. It's only readable by humans. And for the 3 sections, I split out functions, bodies, and Euler's method. We could see that denoted here too. This is how we transfer a skeleton of our program into actual code. So this force of gravity is the same thing that we learned last week, we just copy pasted it onto here. Our bodies is what I denoted before. We have our little star, our sphere. I've indicated some parameters. You could copy these same ones if you want to get the same thing that I have. We did one for our star and one for our planet. And then here's our animation. Now again, like I said before, we have our t, dt, and rate. These are things that we learned in week 2. And then in physics, basically what we're going to do is that the movement of each object is governed by its position, momentum, and force, or its position, velocity, and acceleration. 3 derivatives of position with respect to time. Or sorry, 2 derivatives. And so we're going to calculate the net force on each object, which is going to be the star dot force. So just like how we did star dot momentum or star dot position, force is another attribute of star that's exclusive to star, and so we're basically going to store this vector, which is the force of the planet, or the gravitational force of the planet on the star in the star.force variable, or attribute of the star sphere object, and do the same thing for force. And we're going to update our momentum, which is like we learned momentum plus force times time. Update position, which is position plus momentum over mass times time, and then increment our time. So these are 3 sections of our code. This is fairly similar. This is the homework assignment last week, I believe, or the exercise. You'll see that when we run this, we get our very first cool simulation. This is pretty simple. It's just 2 bodies, one planet is going around one star. You can see how the speed changes as it goes around because its orbit is slightly different. If you want, you can go in and tweak some of these parameters. So with our planet, if we give it an even bigger initial y momentum, let's say 26, then we can see how its orbit is vastly different. Goes along a little different here. If you want, you could try and experiment with using some concepts in physics like centripetal force to try and make it go around in a perfect circle. It's a really cool exercise if you want to try it on. If you want to try it on your own, you could experiment with, let's say, giving the star an initial momentum. Let's call this. Let's give it 10,000. You can see how you could get the entire system to move. Oh, that was way too big. I'm sorry. Oh, because I gave it a position. I'm sorry. Give our star an initial momentum upwards, then our star moves as well. You can see how once it gets back, the entire orbit shifts. And this is it basically for animating two bodies with a gravitational force on each other. But as you know, in real life, like in our solar system, there are way more bodies than two. And to get to that point, to animating that, it's a little more complicated than just adding one or two more lines. And so, before we jump into animating systems with more bodies than just two, we're going to learn something that's going to help us out a ton. I'll explain why later, but part 2 is basically just going to be going over this concept of lists in Python. Now, the goal of computer science fundamentally is just to optimize certain mathematical processes that we're doing, because a computer, of course, can do math like a billion times faster than any human can. So our goal is to make our code as concise and short as possible with no repetitions at all. As a general rule, you should really have to copy and paste a segment of code multiple times. This is why we have loops, so we don't have to write the same thing 10 times if we want a loop that goes for 10 iterations. And we've already put this principle to use in something like our force of gravity function. Instead of doing this full mathematical calculation every single time we want to calculate the force of gravity on two objects, we just call the gravity function f sub g, and the computer does all this in the background. So this is another example of how we're not copying code. Instead, we're optimizing it to make our code more short, readable, and ultimately understandable and more efficient. So when we want to oops. Sorry, I cut to the wrong slide. When we want to store multiple values in a single variable, you'll see why we'd want to do this in the next part. We can use something in Python called a list. Now, I'm just going to run through some of the syntax of it, and hopefully you could learn just by these examples. So, simply, a list is basically something that holds different items or multiple elements inside of it. So to declare a list, you're basically just going to use these square brackets and then indicate however many elements separated by commas. So in this case, I have 3 strings. I store them in the list, this list. This could be any variable. It could be x, y, potato. And then when I print it, I'm just going to get this list with all 3 elements inside of it. Now, a list doesn't have to be strings, it could be numbers, so we could do 7 plus 7 as one of the elements in the list, or it could be Boolean values, so we could do, let's say, true and false. They don't all have to be the same type, and as you can see, we get apple 14 and false. Now, so far, you might not know the benefit of one of these lists. It just stores multiple values in one thing. To access these lists, we can access them based on their index. So this, the way that this list is organized is that each of these have an index. So indexes always start at 0. So apple is going to have an index of 0. Banana is going to have an index of 1, and cherry is going to have an index of 2 in this list. And the way to access that is to just do the name of the list and then square brackets and then the numbered index of which one you want to access. So this list 0 would access apple, because it's the 0 index, and 2 would access cherry. And when we print it, we can see that should print the whole list, apple, and then cherry. Now, the cool thing about lists, in Python at least, they're similar to if you've taken AP Computer Science A. If you're taking Java, then lists are similar to array lists, in that they're changeable, they're mutable, as you would say. What you could do is that you could add things onto the end of the list, and that's what this .append function is going to do. It's going to take this list and it's going to add another item onto the end of it. So before we just have this list with 3 items, index 0, 1, 2. When we append orange, it's going to put a new one, orange, at the end of it, and that's going to have the 3rd index. So what we predict should print when we run this function is first the list with its 3 components. Then we append. This isn't going to print anything. This is just going to change the value of this list to have 4 values now, an orange at the end. When we print it again, it should print the version of the list with 4 values. And then 0 should access apple, and 3 should be 0, 1, 2, 3. It should print orange. And when we run this program, we see that that's what we end up seeing. The one with orange added, 0th index, and then 3rd index. Now that's basically how to declare and add items to lists. One of the other strengths to using a list is when we loop over them, it's a bit easier. So if we wanted to loop over a list, this is a new type of loop that we haven't learned yet. It's called a for each loop. And I'll just talk through roughly what it means. So what this is going to do for x in this list, you can think of it as for each item, which we're going to denote as x in this list, and then we're going to print that item in this list. So just to show you what ends up printing, it should print every single item in this: apple, banana, cherry. And so yeah, every variable, for every iteration of the loop, it's going to assign whatever index, or whatever that iteration of the list indexes to x. And so, yeah, I hope you understand what I'm saying. This is a lot hard to explain. Yeah, again, you'll see that these 3 items are printed, and if we add more, then it's going to iterate over that too. If we want to add another thing, like hello at the end, just to see what happens, you can see that it should print hello at the end of everyone, at the end of all of them. And I've just gone over very quickly and very simply a couple of features of lists, but lists have a ton of other really, really cool features. I'll link a resource below so you could explore with some more examples, but all we need for the purposes of this so far is just how to declare a list, how to append values, and looping over them. And so just as a bit of review, lists can contain any combination of data types. To instantiate them, you're going to use these square brackets. Indexes or lists have indexes that always start at 0, and to access it, you're going to use the name of the list, and then in square brackets, the index that you want to access. You can add items to the end of a list with the .append, and then you could access those with another index. And you can loop over all the items on a list with a for x in. You could change x to for all items, or for all potatoes in this list, and then you could do whatever you want with it. In this case, we're printing it. So in part 3, we're going to take what we learned in part 1, which is animating 2 bodies, and we're going to combine that with what we learned in part 2 with lists to generalize our simulations to n bodies, or any number of bodies. So we can animate, let's say, 3, 4, 5, or even 100 bodies, all dynamically acting on each other, having gravitational forces on each other. So when we have more than 2 bodies in our system having gravitational forces on each other, each body is going to have another vector for each other body existing in the system. So we could focus on this bottom one. It's going to have a gravitational force towards this planet, and it's going to have a gravitational force towards the right planet as well. And the net force on this bottom planet is going to be the sum of these 2 vectors. So you can do the tip-to-tail method, and you can find that its net force should be something in this direction. So in physics and astronomy, when we're trying to code this, this is something called an n-body simulation, or any number of bodies, or n meaning any number of bodies. You could look more, you could research this more on your own. And it's basically defined as like a dynamic system of particles, and it's under the influence of some physical forces. So this could be collisions, this could be gravitational forces like what we're doing now, and it could be electrostatic forces, magnetic forces, really anything. And this is used really, really often in astrophysics. It's a really big part of the field. It could be used as something as simple as 2 3-body systems like this, or the Earth, Moon, and the Sun, all the way to doing large-scale cosmological things like structures of the universe, galaxy filaments, galaxy halos under the influence of dark matter, and star clusters, all sorts of stuff. It's super, super cool. But for right now, what we're trying to learn is how can we implement this idea of an n-body simulation into our code using our force of gravity thing. So of course, when we actually start implementing it into code, you don't have to look at this right now, but we're obviously going to have to, let's say we have, and when we move from 2 bodies into 3 bodies, we're going to have to declare more spheres in VPython. That's just a given, and we're going to have to give it a new position, a new momentum, a new radius, and a new mass. That's a given. But when we move to animating with Euler's method, like what we see here, this was in the part 1 glow script document I showed you. This is the same Euler's method animation section, just put on the screen here. When we start animating things, your first instinct might be to just add new lines. So let's say we have star, planet, and let's say our new thing is a comet. So your instinct might be to do comet.force equals fg comet, and then star, comet, planet. But remember, like what we said before, each planet or each body is going to have multiple forces acting on it, and its net force is going to be the sum of all these forces. So really, what we're going to have to do is calculate a net force on each body. So let's say in this case we have planet 1, 2, 3, and then a comet. The net force on the star is going to be the force of planet 1 on the star, planet 2 on the star, planet 3 on the star, and it should be the comet too. I forgot to mention that. Probably because in this case the mass of the comet is negligible. And you're basically going to have to add all of these. And then when we move on to the momenta case, you're going to have to, the net momentum, or we're going to have to update the momentum of each and every one, and we're going to have to update the position of each and every one. And as you could see right here, even with just 5 bodies, it gets like disgustingly complex and tedious to type out on your own. Here's the 2 code segments side by side, so you could kind of see how just by adding 3 more bodies, it gets a lot more complicated. And this might be manageable. I managed to type this out on my own in small numbers, but it's completely normal to have systems with like 10, 20, or even hundreds of bodies, if we're counting stuff like asteroids in an asteroid belt, which is what we're going to be covering next week. So once we get to really high numbers and really complex systems, it's not feasible to just type out planet 4.force, planet 5.force, planet 100.force, and type this plus this plus this. That just gets annoying. And like we talked about in part 2, the point of computer science is to optimize our code, is to make it simple, readable, and to do tasks much faster than what we'd have to do manually. So this is where we can apply what we learned about lists and start putting our bodies into lists. So this is a new upgraded skeleton structure. So this is the old one in gray. This is our new one, and I'm pretty much just going to compare what we're changing. So over here at the beginning, declaring the functions is going to be the same as before. It's just our force of gravity with a little change, although I'll go over that later. When we declare our bodies, instead of making a star variable, planet variable, all these things, I'm going to start with an empty list called bodies, and then I'm going to append spheres to those. Remember that in a list we could have any type of data type. We could have numbers, integers, strings. Numbers and integers are the same thing. Sorry, we could have integers, strings, booleans. We could also have spheres or boxes or anything. Because remember, in VPython, a sphere is just a certain type of object. It's like a variable that we could dump some. It's a variable, so we just append that onto the bodies list, and we can have bodies represent a list of all the bodies in our system. And then at the bottom, when we animate with Euler's method, this is where our optimizations and our simplifications start coming in, where we could just use what we learned before, or for each loop, to just say for every body, or for each body in the bodies list, and we're just going to calculate our body.force. And this is going to take, like what we had before, this is going to take these 5 lines and condense it down into like 1 or 2 lines, or usually just 2 or 3 lines. We could start putting this to use in our actual code, which I'll go over to now. So here is an edited version of the program that we talked about in part 1. It follows the same skeleton structure that we just went over with function, bodies, and our Euler's method animation. And this time we have 4 total bodies. And this is a version of that, but now we're simplifying it, or integrating lists to optimize it. So at the beginning we have our force of gravity function, same as always. I've added this, if you noticed. I'll go over this later. But basically what it's doing is that, let's say you pass the b1 and b2 that you pass to this function are the same exact object. The force of something on itself is 0. So we need to add this because the difference in their positions is going to be 0. and then we're going to be dividing by our vec. We're going to have a divide by 0 error. So at the beginning, we're accounting by that by just saying, well, if the position of one object is the same as the position of the other object, in other words, if they're the same exact object, if they exist at the same exact location, then the force vector that we're returning is just going to be 0, 0, 0. Or in other words, the force of a body on itself is 0. Moving on to the body section, like we said in our skeleton structure, we're going to start by declaring an empty list called bodies, just denoted by these two brackets, and then we're going to start appending different spheres onto bodies. And I've put a comment up top for what each of these is going to be. So we're going to start with our star, our yellow star, which is the same as the thing from demo 1. I've changed a couple of small numbers, but it's essentially the same exact thing. We're going to append our first planet, which is going to be green, which is the same from demo 1, and then we're going to append 3 more new things that I'm adding right now: a red planet, an orange planet, and a comet. And the order of these is going from center outwards. So sun is at the center, the comet is furthest outwards. And you can ignore this last section. So now after the computer reads this line, effectively what we have is a list called bodies with 5 total objects. Index 0 is going to be our star, index 1 is going to be our planet, and onwards until we get to index 4, which is our comet. So 5 total objects stored in this bodies list. Then once we get to our Euler's method for animation, this is where we could start, all this is the same as before, this is where we could start implementing our for each loops into optimizing this. So this is for calculating net forces in a moment. I'm actually going to skip this for now, and I'll come back to this later. Let's start with our momentums. So as you might remember from week 2, the equation for updating our momentum is just going to be our new momentum is going to be equal to our old momentum plus our force times our change in time. And that's because force is defined as a change in momentum over a change in time. But now, even though we have 5 bodies, instead of having to do, well, the momentum of the sun is equal to the momentum of the sun, and then the momentum of planet 1 and the momentum of planet 2, repeating that over and over and over again, we could just loop over for every single body in bodies. So remember, we had 5 bodies in the bodies list, so this is going to run 5 times. For each B, we're going to update its momentum like this. And so the first time this runs, B is going to be the sun. It's going to be index 0 of the bodies list. It's going to be the sun. Then we're going to update the momentum of the sun. Then it's going to loop back, and it's going to move on to the next object in bodies, index 1, which is the first planet. It's going to update that momentum, and it's going to loop again. It's going to move on to planet 2, and it's going to update its momentum, and so on and so forth, until we update the momentum of all of them. And again, whereas before, it would have taken like 5 or 6 tedious lines, copy-pasting a lot of code to do this. Now with just 2 lines, we managed to update the momentum of all of the objects. And the same principle applies for the position, except for instead of updating the momentum, we're updating the position. And as we learned, the formula for that is position is momentum over mass times et. Momentum being mv, or mass times velocity, divided by the mass, which just gives the velocity. Velocity times time is a change in position, adding our change in position to our original position to get our final position. Now, this is where I'll come back to calculating the net force at a moment. So whereas these two are updating a position, this is calculating the net force, because the momentum is just one vector that we're dealing with, and the momentum and the position is just one vector for each planet. When we're dealing with the net force, like I showed you in that little diagram with those 3 planets, we're adding together multiple vectors that represent the force of gravity on each and every planet. So that's going to require something a little more complicated. And this is where we're going to apply something in computer science called nested loops, and this is going to come up a lot. Essentially what we're doing, I'm going to explain this. You don't have to understand this fully. I'm going to go back to our slides and give you a slightly easier explanation. But just to go over the different parts of a nested loop, see how we have for every B1 in bodies and for every B2 in bodies. So this is what's going to be, and notice how this loop sits inside of this. So every one time this executes, this is going to execute multiple times, then this is going to loop back here, and it's going to execute this multiple times, and it's going to loop back. I'll give you a better visualization, but this is what we call a nested loop. This is our outer loop, and this is our inner loop. So I've made a little diagram kind of thing on slides to show you a little bit more the intuitive side of nested loops. So this is the system that we had before, minus the comet. This is just a sun, planet 1, planet 2, and planet 3. These are all objects that exist inside of our bodies list. And we have our outer loop and our inner loop. So when we have that nested loop kind of thing, this is essentially how it's going to run. So first, of course, it's going to start, the outer loop is going to start with the first object in bodies, which is going to be the sun, because it has an index of 0. And then it's going to get to the inner loop, and it's going to calculate the force of gravity of the sun on the sun. And of course we know that's 0. That's why we added that first line in our, that's why we added that extra line at the beginning of our force of gravity function, so that it knows that the force of an object on itself, if it's at the same position, then the force on itself is 0. And then what it's going to do is that within the same outer loop, it's going to move to the next one in the inner loop. It's going to calculate the new force of gravity, and it's going to repeat that for each object inside the inner loop. And then at the end, we're going to end up with all these forces of gravity, and we're essentially just going to add these all together, and that's going to give us the net force on the sun, which in this case, these are just random numbers, but this is 225 newtons. Of course, in real life, it's going to be a lot greater, but these are just sample numbers. And then what's going to happen is that we loop through all of the inner loops. So we've satisfied all of these. And so we're going to, this inner loop is going to complete running because it's gone over all of the bodies in our bodies list. And then we're going to move on to the next item in the outer loop. And then it's going to start this process again, where we start with the first item in the inner loop, and then calculate the force of gravity, second item on the inner loop, and so on and so forth, until we calculate the net force on each one of these objects in the outer loop. And so, going back to our code, we see that this is our outer loop, this is our inner loop. Effectively what we're doing is that we're going to be calculating the force on B1 due to all the other bodies denoted by B2. That's what we have here. The body whose net force we're going to calculate is B1, and B2 is going to be the bodies that exert a gravitational force on B1. So really quickly right here, we're starting where we're saying that each body starts with a net force of 0 here. We're setting its initial force equal to a vector that has 0, 0, 0. And then here we're just calculating the net force by doing its force is equal to its old force plus the force of B2 on B1. That's going to loop through all these planets, and it's going to have that effect like what I described in the slides of calculating the net force on B1 by all the components of B2 on B1, and that's effectively going to calculate the net force at a moment on a planet. And so, when we run this function, we'll see that, yay, finally we have our 5 bodies all acting on each other, and we finally have our first cool solar system simulation with multiple objects. And we did it in a relatively small number of lines instead of having to write new lines for each and every one of these. And if you want to add, I encourage you that if you want to try with your own bodies, if you want to have multiple asteroids coming in, some with a wider orbit, if you want to have 2 asteroids, if you want to try make a binary star system, which is 2 stars at the center of a solar system, if you want to add more planets, if you want to try representing our own solar system, you could do that, and all you need to do is just append another sphere into the bodies list, and that'll make the process a lot easier than having to append the body and then calculate and then add new things for net force and update all the old ones. And so this is how applying array lists to our n-body simulation simplifies the entire process a lot. And we get this little thing. It's a little trippy when you rotate it around. And by the way, if you're running this on your computer and you're finding it, that's cool. If you're finding that it slows down a lot, then what you could try, oh, this is cool, I think. Oh no, I missed it. But see how the orange planet threw the red planet out of orbit, and now the comets, the comets, this is an asteroid, sorry, it's a comet, its orbit has gotten a lot shorter. What was I? Yeah, I was saying that, if this is running really slow for you, there are a couple of things that you could try doing. You could try making the, dt a lot smaller. You could try making the rate smaller. As a general rule, I try and do, 1 over 5 times dt. I find that's what I use based on my dt, but if you want to decrease your dt, then you have to adjust your rate accordingly to make it not go super fast. And it's going to be a little more choppy, but it should run a little smoother like you're seeing now. It's running a little slow right now because I have my recording software open. But yeah. Now, while we let this run for a little bit and see this chaos unfold, I'll talk about some exercises that you could try on your own. And I think this is the fun stuff, because now we're actually applying what we learned. So my challenge for you, I'm just going to have one main one, and it's to see if you can make a program that generates 5 bodies, not necessarily your sun, planets, just 5 random bodies with completely random masses, positions, and momentums within a certain range. For example, like the mass needs to be between 1 and 5, and set those into motion and see how those move around each other. And then as an added little challenge, try to randomize their colors too. Hopefully you'll get a result that's like super cool to look at and play with. I made it on my own recently, and sometimes I just run the simulation over and over again for like 20 minutes at a time instead of paying attention in class. And of course, if you need help or tips, or you need any help or tips with this, feel free to message me on Discord. I'm always happy to help. And just to talk about what we're doing next week might be our last lecture on gravitational forces, where I'll go over the solution to this homework assignment, or this exercise that I just posed to you, along with some other cool applications of the gravity function, like applying it to black holes to model the phenomenon of spaghettification, and modifying our gravity force function into an electrostatic force function to replicate the gold foil experiment that led to the discovery of the atomic nucleus. So definitely look forward to that. Oh, and there's one last thing. If you want to make it so your trails don't exist forever, you could add like a retain number. So retain equals, if you use a good, we'll try 10. Probably shouldn't be on the star. I'll demonstrate it, let's say with the green planet. See how it only exists for a short time afterwards, and that'll make it so it's less cluttered if you want to let the simulation run for a long time and see what shows up. So as always, part 4 is our regular feedback section. Here's a regular feedback form. It should take 3 to 5 minutes to fill out, or you can just message me directly on Discord to tell me what you thought of this lecture. Make sure you're in the Discord, invite your friends. You don't have to do any of these assignments. I'm not going to message you saying, why haven't you watched my lectures or submitted any homework? We have some fun conversations in there every once in a while. We post some memes sometimes, do some stupid stuff. You can also watch this this lecture from our website, and on it there's an integrated IDE as well. Now to leave off, that's it for our week 4 lesson. To leave off, here's a little application of that homework assignment I told you with the 5, that wasn't supposed to happen. There are 5 randomized bodies. You can listen to some nice music and admire it for a bit as a way to close off this lecture. Alright, bye-bye.